All right. Hello? Hello? Okay, hello everyone. My name is Joshua Garcia. I'm an assistant professor at the University of California, Irvine. And I am session chairing paper presentations P13 on security. We have a combination of technical track talks and software engineering and practice talks. The first talk will be given by Changwei Zhou. The paper is entitled Burn After Reading, a shadow stack with microsecond level runtime re-randomization for protecting return addresses. Changwei, feel free to start when you're ready.
Hello?
Hey, Changwei, yeah.
Yeah.
I can hear you.
Yeah. Hello, everyone. I'm Changwei. Today, I'm going to talk about how to protect return addresses on the core stack. This is a joint work with my supervisor, Professor Jinlin Xie. The new technique we provide is a shadow stack with microsecond level runtime randomization. The title is a little long. The term burn after reading in the title means that our technique is very fast, such that it can be done frequently to invalidate the disclosed information. First of all, I will give a simple example to show how a buffer overflow vulnerability can be exploited to hijack the control flow. As you see on this slide, the get function called at line
Changwei, your
3.
slides are not showing.
Not showing, yeah, but I share the slide. Yeah, sorry about that. But I checked. Yeah, does that work?
Yep, we can see it now.
Yeah, sorry about that. Yeah, sorry. As you can see on this slide, at line 3, the get function reads input from the user, but it doesn't check whether the buffer at line 2 is large enough. So a malicious user can provide more data than the buffer can support. So the return addresses on the core stack can be modified by the malicious user. So when the function returns, the control flow will be hijacked. By the way, there's also a format string vulnerability at line 4, which can lead to information disclosure. We will discuss this later. So there are several solutions to mitigate this problem, including code randomization, control flow integrity, and shadow stack. The shadow stack hides the return addresses in the hidden stack. It relies on the hiding of the location of the shadow stack, so it's vulnerable to information disclosure such as format string vulnerability. As shown in this slide, the number of information disclosure vulnerabilities reported on the CVE website has risen quickly in recent years. So when code sections are remapped at runtime, all code pointers need to be updated. So there are some challenges in runtime randomization. First, runtime code pointer tracking is very expensive. For example, the state of the R word runtime ASLR, which was published on NDS 16, spans several seconds to conduct a round of randomization. Secondly, code pointer checking is difficult. Although a low false positive has been achieved, it's still very hard to avoid. Third, to mitigate information disclosure such as format string vulnerability, runtime randomization should be conducted as frequently as possible. That is, it should be very fast. In this slide, we give the motivations of our research. First, we want to provide a microsecond level runtime randomization mechanism for protecting return addresses on the core stack. Second, we observe that by adding one level of indirection, we can randomize the return IDs rather than remapping code sections. In this way, we do not need to do the runtime time-consuming code pointer checking anymore. As a nice side effect, we also obtain an ability to catch the potential attack instantly. Third, our technique can be conducted frequently at any time to make the leaked return IDs invalid. That is burn after reading. The term appeared in the title of our research. We named our prototype BALA. That means burn after reading for protecting return addresses. We have implemented in the LLVM compiler tool train. Fundamentally, BALA is an assembly instrumentator. In this slide, we show the basic idea of runtime randomization. For each return address on the core stack, it has a corresponding return ID on the BALA stack. It's similar with the traditional saddle stack, but we save the return ID rather than the return address on this saddle stack. So we call it BALA stack. When the return address is pushed on the core stack, we also store its corresponding return ID on the BALA stack. At any time, we can generate a random value and add it to each return ID on the BALA stack, as shown in this rule. In this way, all these return IDs on the BALA stack can be randomized. We also can hook all the input or output functions, including the socket functions such as guess. For example, when you call the guess function, we can hook it like this. We call the randomize method here before we call the original guess. So anytime, so the runtime randomization can be triggered when these functions are called. Here is an example to explain our runtime randomization. The burn after reading at T3 makes the gadget 204 at T2. The attack goal at T2 stale, that means invalid, such that the attacker cannot successfully hijack the control flow to the ROP gadgets he needs. It's very important to know that we do not need to reorder or hide our mapping table at a long time. This design makes our solution extremely fast. In this slide, we give an example to show how to instrument the code sections. In this slide, we show how we instrument the data section. I think I should be speed up. When we evaluate our solution, we show its efficiency and effectiveness. Basically speaking, the attack success rate in guessing a correct return ID is only 1 out of a million. Suppose the mapping table size is 1 million. And the overhead of our instrumentation is similar with that of the saddle stack. but the instrumented binary size is a little larger than the traditional shadow stack. The time spent for randomization usually is only 2 or 3 microseconds. Here is the basic the statistics of our evaluation on the 19 C or C++ spec benchmarks. More details can be seen in our paper. We also give a proof of concept attack, and we compare with the traditional shadow stack. As shown in this slide, our solution can detect the lob attack. Basically, our solution is a 3-in-1 approach. It combines shadow stack, control flow integrity, and long-time randomization together. We also open source our solution. If you are interested, if your review, okay. And this is our conclusion. It's a microsecond level long-time randomization. So, any question?
All right, yeah, thank you, Chang-Wei. So I'm not seeing any questions pop up on Slido yet because there is a 1-minute delay between Clouder and Zoom. Please try to send in your questions early. Since we're also maybe pretty close to being over with your talk, Chang-Wei, I think we'll maybe move on soon. Yeah, I think it's best we just move on. Okay, thank you again, Chang-Wei.
Yeah, thank you very much.
The speaker for the next talk is not available. So we're just going to get ready to play his pre-recorded video. I assume it's a he, sorry, I'm not sure they. The person's name is Andrew Santosa. This is a software engineering practice talk entitled Automated Identification of Libraries from Vulnerability Data. Yes, feel free to start the video.
Good evening, everyone. Today I will talk to you about automated library identification from vulnerability data. I am Andrew Santosa, and this is a joint work of myself with Chen and Sharma from Fedacode and with Professor Low from the Singapore Management University. The topic of this talk is in the context of software composition analysis. So firstly, I will discuss about it. Secondly, I will discuss our approach of identifying vulnerable libraries from NVD entries using the FastSML algorithm. Thirdly, I will show some of our experimental results before concluding this talk. So open source libraries are very widely used in today's software development. They have contributed significantly to speed up and lower the cost of software development, but the impact of security vulnerability in open source libraries can be severe. So if you develop an application which uses open source software libraries, you would wonder if your application uses vulnerable libraries, either directly or transitively. So this is the problem that software composition analysis, or SCA, solves. It analyzes your application to automatically find out the vulnerable libraries it is using. The core of software composition analysis is a library of vulnerability database, which contains the information of open source libraries and their vulnerabilities. The library vulnerability database is created by security researchers using data from various sources, including the National Vulnerability Database, or NVD, JIRA tickets of various open source software Baekje reports, GitHub issues and pull requests, and commits and mailing lists. One of the tasks that the researchers need to do is to associate vulnerability data from the NVD with open source libraries that are vulnerable. This talk focuses on helping this process, which is specifically to automatically recommend library names related to an NVD entry. Associating NVD entries with library names is not straightforward. Here we show the textual part of the data for CVE 2015-7318 retrieved from the NVD. This vulnerability actually belongs to the ZOP2 Python library. However, this library never mentioned in the textual data. So if we take a closer look at each NVD entry, there is actually a specific component of it that seems to refer to library names. This component is a CP configurations, which is a regular expression containing product names, with an example shown here. Here the product name is e-commerce. The product name may be a library name, and it can be used as a matcher for direct matching with a library name in the library vulnerability database. Unfortunately, such direct matching has a low prediction performance, where the average F1 score is only 0.24 across all NVD entries. So since direct matching is ineffective, we try to use a machine learning approach. Here we treat our problem as an instance of extreme multi-label learning, or XML, where the problem is to match your data into a large number of labels. Here we have close to 8,000 library names to be matched against. These libraries are the labels in our case. There are several attempts at solving this problem in the literature. We use the approach called FastXML by Prabhu and Pharma, which was presented in the 2014 KDD conference. This approach is often cited in the literature, and for our system, we use the FastXML implementation by Referfer, which is available on GitHub. Our system is already used in production where, as shown in the UI here, when given an NVD entry, the system recommends a number of libraries of potential matches, each with its own score, which is the likelihood of match. We now briefly discuss the features of the FastXML algorithm. Importantly for our discussion later, it is basically an algorithm that builds an ensemble of trees of the feature space. The root of each tree represents the whole feature space, and the leaf represents a small subset of the feature space. When predicting, the label score is the arithmetic mean of the label score across all trees of the leaves the input data belong. We now discuss how we build our training data. So here we have two data sources, the NVD and the SCA library vulnerability database, which is basically a mapping of the CVE IDs to the vulnerable library names. We join the two data sources using the CVE ID, resulting in almost 7,700 label data items. Now let's discuss our experimental results. The extreme multi-label learning or XML problem is about finding the more relevant subset of labels, so it doesn't make sense to use performance measures for traditional binary classification. Instead, in the literature, the ATK performance measures are commonly used, which includes precision ATK, recall ATK, and F1 ATK. The precision ATK is the average of the number of correct predictions among the k highest scoring labels divided by k. The recall ATK is the average of the number of correct predictions among the k highest scoring labels divided by the number of labels for the CVE ID. F1 ATK summarizes both by taking their harmonic mean. On the right-hand side of this slide, we show a small experiment that we had done using only the matches as feature that is given to the FastXML algorithm. Recall the matches are the product name in the CPE field of the NVD data. As you can see here, the performance is quite low, so this approach is ineffective. In the next experiment, we use all features of NVD that we listed before, not just matches, and here we show some effect of data cleaning. First, we have basic data cleaning, where we basically remove non-alphanumeric characters. Second, we apply non-noun removal, where we remove non-noun words. Third, we apply frequent words removal, where we remove a word if it appears in some percentage of more of the NVD entries. We experimented with 30%, 60%, and 90% frequent words removal, and we discovered that basic cleaning with non-noun removal and 30% frequent words removal gives the best result and is what we use in production. As I mentioned before, FastXML learns an ensemble of trees where each one is a different model. Using more trees may improve prediction performance since this reduces randomization bias in the algorithm. However, multiple trees also enable parallelism for training and production, but it can also worsen running time due to overhead. So on a node with 16 cores, we did an experiment with 32, 64, and 128 trees, and we used 64 trees in production since it seems to provide the best performance without too severe execution time penalty for training and validation. So the two rows labeled T of S and V of S here show the training and validation times for each configuration. Over time, the security researchers label more data, and we can use the extra data to train better model. However, before we deploy the new model into production, we want to confirm that the newly trained model has a better performance than the existing model in production. So we compare their performance in two ways. For the first comparison, we simply compare their validation performance when they were trained. For the second comparison, we compare their performance for the same dataset, which is a random half of the dataset for training the new model. The table here shows the experimental data for production model trained in July 2019 and a new model trained in September 2019. For training time comparison, there is a decrease in precision of new model, but average F1 at K still improves by 1.09%. For comparison with the same dataset, the performance measure confirms that the new model outperforms the production model, raising confidence for it to be to be used to replace the production model. So to summarize, we had discussed a machine learning system to predict related libraries for each NVD entry. We modeled each problem as an instance of the extreme multi-label learning, XML, due to a large number of labels. We use fast XML algorithm, and we developed a recommendation system that we already use in production. At the time of writing, which is late September 2019, our model has F1 at 1 score of 0.53, with average F1 at K score of 0.51 for K 1 to 3. For future work, it may be possible to try to consider deep learning approach, as some literature claims to better and fast XML performances in deep learning, but this requires more data and more research. Thank you.
Okay, so Andrew Santosa isn't actually here. That was a pre-recorded talk from him, but we'd like to thank him nonetheless. So he's not here to take questions, so let's simply move on to the next talk, which is a technical track talk will be given by Yude Bai. The paper is entitled Unsuccessful Story About Few-Shot Malware Family Classification and Siamese Network to the Rescue. Yude, when you're ready, feel free to start.
Okay, can you hear me?
Yes, I can.
Okay. And can you see my slide?
Yes, I can see your slides.
Yes, there we go. Hello, everyone. I'm Yude Bai, coming from Tianjin University, and I'm very proud to have this opportunity to introduce our work. At first, here are two figures. We can find the sharp increase of malware. Grouping malware with common behavior into families is an effective way to battle the fast growth. Here are several malware family datasets, such as Genome, GB, AMD, and its variant. We named them M1, M2, M3, and M3S. We can observe a long tail distribution of family size on the left bar chart. We box the long tail part of each dataset, and we refer to all datasets as the all. Then we create a downsampling dataset for such 4 datasets with a downsampling strategy. Taking M1 as an example, we downsample the large families to 100 applications for each large family, and the medium families to 10 applications for each medium family, and the small families remain intact. As a result, we get 4 local balanced datasets. We name them as the part. We can see the changing of them from all to part. We manually select permissions, critical API calls, and ICC as malware features. All these features can be available on our GitHub. We formulate our task as a multi-class classification problem. At first, we will do some experiments about normal learning method, that is no Siamese network. Malware applications are represented as a one-hot feature vector after reverse engineering, and then they are sent into a machine learning classifier for training and testing. So the RQ1, or we want to evaluate overall performance of such datasets, that is NOSIO, and we want to evaluate the impact of downsampling, that is NOSI part, use part dataset. As it's shown in this figure, the R give F1 more than 0.8, which means a very good performance. But when comparing the F1 value of same classifiers in NOSI and NOSI part, we find downsampling cannot address the data imbalance well. They're very close. Further, we investigate the performance across large, medium, and small families, 3 different scales. The green lines in this feature reveal the performance is inconsistent. We can see a clear decreasing trend from large families to the medium and then small. On the other hand, we observe the F1 variations on the medium and small families are large, which means per generalizability, downsampling cannot work well. So the conclusion of RQ1 and RQ2 here, when we look into the prediction performance for different scales, the unsatisfactory performance, especially for small families, emerges from the shadow of the glory. So how to rescue it? This is our proposal to rescue Simon's network. It consists 2 steps. Step 1 is to train a MLP-based feature extractor about Simon's network. Step 2 is to classify with this feature extractor. Not when we're training Simon's network, it requires malware application pairs that are positive and are negative pairs from the same or different malware families. Here we create the datastate of pairs from the downsampling datastate or part datastate, mainly because of the resource limitation. So here in RQ3 to explore effectiveness of Simon's network. That is psi part. Its comparison is not psi all. Psi part obviously outperforms no psi all in all combinations, and it also gains smaller F1 variation. Same to RQ2, we then set experiments on different family scales. Taking M3S as an example, we can see the performance boost by psi parts in all cases, 16 cases. The red arrow also shows that the smaller the family is, the larger it can boost. The green lines here is to explain the psi part can narrow the performance gap across family scales. See the less steep lines. At last, we want to know, without Simon's network, can the only MLP-based feature extractor achieve the same performance boost? This figure shows the framework of this RQ. The MLP network here had the same network structure as the MLP network in Simon's. See this figure. The green lines show psi part achieves higher F1 than others in all cases. That is to say, MLP-based feature extractor alone cannot result in the performance boost. Here are 3 contributions of our work. To the best of our knowledge, is the first to systematically look into the imbalance issue on the performance and generalizability of malware family classification. We also reveal neither downsampling nor MLP-based feature extractor alone can address such 2 issues. We confirm the superior performance of Simon's network, especially for the future malware family classification at last. All experiments related information can be available on our GitHub. Thank you for your listening.
All right, thank you, Yude.
Okay.
So while we're waiting for potentially questions to show up on Slido, I was wondering if you could explain more as to the theory why a Siamese network is good for improving these malware classifiers. I'm not sure I quite understood that.
Okay. You can see in this slide. we can see that the performance is the performance is poor because mainly because of the such as the medium families and the small families. So if we can use Siamese network to boost the performance of medium and small families, we can boost all the overall performance.
Okay. So, and that's a general property of these Siamese networks. If you have labels for which there are a small to medium number of instances, it has a tendency to boost the, I guess, accuracy for those particular types of labels. Is that what you're implying?
You mean my future work?
No. I'm talking about the nature of the Siamese network.
Nature of Siamese network. I think I'm sorry. I think the performance boost is coming from we have created plenty of pairs. So this creates more opportunities for this structure to learn the common features that malware applications in the same family share, compared with learning from malware application individually in the normal model learning method.
Okay.
Okay.
So I have one more question. So
Okay.
for AMD, so genome, I'm guessing is the old Android malware genome. What's AMD stand for here for your data sets?
It's data sets from AMD. It is AMD. AMD has 24,478 malware applications in 71 families. It is a paper in 2017.
Okay.
Okay.
Okay then. So I'm still not seeing any other questions pop up for now,
Yes.
and I don't have any additional questions at the moment. So I'd like to thank you one more time, Uday, and
Okay.
and we'll get ready to move on to the next talk. So our next speaker, also from the technical track, is Shengjian Guo. The paper being presented here is entitled Speculative Symbolic Execution for Cache Timing Leak Detection. So Shengjian, take it away when you're ready.
Sure. You can see my share screen?
Yes, I can.
Sure, cool. Hi, I'm Daniel from the security team of Baidu Research. Today, I'm going to talk about our Speculative paper. It's a joint work with my colleagues from Baidu and our collaborators from Penn State, Ant Financial, and Nanjing University. So cache is a high-speed storage between the CPU and the main memory. Here, if we ask a CPU to read a variable, it will be very fast. You first query the cache. If the data is already in cache, the read operation will be very fast. If the data is not in cache, the query will go to your main memory to get your data, and it is very slow. And such cache timing difference may leak sensitive information. In this project, our key insight is that a time leak-free program may still leak sensitive information when running under speculative execution. due to memory visits in a speculative flows. And this figure shows a simple program which has low timing leaks. The program body has several variables, a while loop, a if-else branch, and a memory load at the end. It takes k as a sensitive input, and disclosing the value of k by cache timing is a leak. So on the right side, we have the control flow of this program. There are two program passes. We call the left one as P1 and the right one as P2. The only difference between them is from the store instruction, where P1 stores V1 and P2 writes to V2. So next, we inspect the cache behavior of our two passes. Here we use a 256-byte fully associative cache with the LRU replacement policy. Each cache line has 1 byte, and there are 256 cache lines in total. So if we run past P1, the while loop will load the array into a cache. The cache was initially empty, so all these memory load operations cause cache misses. Next, we read the variable k and map k to your cache. It is also a cache miss. Then the store operation will map v1 to cache, also a miss. And finally, we load sk. At this point, array s and the variable k are already in a cache, so reading sk must got a cache hit. Now we go to path P2 to repeat the cache analysis and list out the cache behavior of each instruction in the table. We compare the listed results between P1 and P2 and find that path P1 and path P2 have the same cache behaviors. So we draw a figure to show a relationship between cache timing and the sensitive input k. We can observe that the execution time is always very similar on any path with any sensitive input k. So the attacker cannot infer k's value due to always similar execution timing, and there's low leak. But what if we execute a program under speculative execution? Is it still safe? Let's consider a possible speculative execution scenario. We can make the CPU to predict the left branch is likely to be taken, but actually we execute path P2. Then line 7 may execute before we really goes into the P2 branch because of the speculative execution. And we use the red dotted line to show a speculative flow. So if such speculation happens, how about the cache behavior? Again, the while loop will map array S into cache. Next, we speculatively execute line 7, which maps V1 to your cache. Then we go to else branch, which use K and store V2. Now V2 will replace S0 from cache because S0 is in the least recently used cache line. And finally, we'll reach load sk. However, its cache behavior might be a miss or a hit because S0 is no longer in the cache. And if k equals 0, it will be a miss. If k is not 0, it will be a hit. Again, we can measure the timing and draw a new figure. We can conclude that if the execution consumes obviously longer time, then k must be 0, because this unique situation only appears if the analyzed speculation happens and k equals 0. So there's a new leak due to speculative execution. And from this example, we found that there are 3 challenges to identify such a leak: the harmful speculative flow, the cache state, and the specific input value. In our work, we propose a small execution-based method. For challenge 1, we develop the speculative modeling, and for challenge 2, we develop the cache state modeling, and for challenge 3, we develop the cache behavior analysis. So by integrating them together, we propose our speculative small execution. And the 3 new components are main contributions of our method. So specifically, given a program, our method uses small execution to systematically explore paths. And with the speculative modeling, we generate new symbolic state to represent speculation. And at memory operations, We use cache state modeling to model cache hit situations by the SMT constraint. And for each memory visit, we use the cache behavior analysis to search for sensitive input. So if the cache timing leaks really exist, we output them. Otherwise, we continue symbolic execution and until all program states are explored. We conducted experiments on a set of real-world CIFO programs and a spectral V1 code. In total, we collected 15 programs from 7 public repositories. And they are typically not large programs, but very computation intensive. And we used 3 different set associative cache settings and focus on 2 timing leak types. In total, we found that 9 programs are leakage-free under all 3 cache settings, and 6 programs have leaks under at least 1 cache. In the detected leaks, 43% are divergent leaks, and the rest 57% are opposite leaks. We also compared Speculative with the state-of-the-art abstract interpretation-based method. Experiments show that they have consistent results in 8 benchmarks, but Speculative identified 2 false positives from that method. And moreover, Speculative also can provide detailed leak locations and the speculative flows for in-depth study. We also developed several optimizations in Speculative. Our results show that the optimized version saves about 20% of constraint size, but almost 70% of analysis time. So due to the speed up, our optimized Speculative detects more timing leaks within a given time bound. So finally, we come to our conclusion. We proposed a new symbolic execution-based method to detect cache timing leaks due to speculative execution. And the Speculative has 3 new components for analysis. For future work, we need more efforts to exploit the timing leaks in depth in practice. And thank you for listening.
Okay, thank you very much, Xingzhen, for that talk. So let's see. Okay, great. We have some questions. So the first question asks, since Intel/AMD do not release any info about their CPU's cache eviction algorithms, do you reverse engineer for your cache specification?
No, we didn't do a reverse engineer work. We just use some existing specifications, and we try to set a specification as close as to the Intel, I think, Skylake CPU series.
Okay. And next question, is this work open source or will it be?
No, it's not open source because the problem is our company's policy. We cannot open source as soon as possible. We need some more works for it.
Okay, so you won't open source, or you can't, or there's a plan to? You can't do it now, but is there any plan to later?
Yes, I cannot do it now, but we are planning to polish the tool and maybe in the future we'll open source it.
Okay, okay. Let's see. Another question. Have you considered multi-level caches?
Yeah, that's a good question. And in this work, we didn't consider like L2 or L3. We just abstract everything as like the L1 cache. Yeah, that's a good question.
Okay. The follow-up question to that is it real hard? Is it targeting real hardware? I'm not sure what it means by real hardware here, but maybe you do.
Do you mean real? So are you asking, are we using the real hardware for experiments or?
In relation to multi-level caches, it seems.
So can you repeat your question, Josh?
So this is a follow-up to have you considered multi-level caching? The question is it targeting real hardware? I'm not sure what real means, and if you're not either, we can move on.
Okay, I can give a brief question. we are not targeting real hardware now. So that's like abstraction of the L1 cache. And that's a good question.
Okay, got it. All right, thank you again, Sheng Jen. So, okay. The final speaker for this session will be giving a talk in the software engineering and practice track. The speaker's name is Ming-Shen Sun, and the paper here is entitled Building and Maintaining a Third-Party Library Supply Chain for Productive and Secure SGX Enclave Development. Ming-Shen, go ahead when you're ready.
Okay, hi everyone. My name is Ming-Shen Sun. It's my pleasure to present our work building and maintaining a third-party library supply chain for productive and secure SGX enclave development. And this is a collaborative work done by Baidu Baidu Security Research Lab. Okay, a little background first. As we all know, a lot of concern have emerged regarding to the correct practice of handling people's personal data by the big data industry. More and more regional government regulation has been deployed to restrict IT service provider collecting, storing, and manipulating large volume of private data. As such, people have been working on different solutions to privacy preserving computation technologies. One of the major players in this competition is hardware-based trusted computing, with a root of trust embedding to CPU chips during hardware manufacture. Software vendors encapsulate code handling sensitive data in the so-called secure enclaves. Secure enclaves encrypt entire memory chunk with hardware provide key. Data is encrypted only in CPU packages, and the enclave can remotely prove their trustworthiness to users without relying on infrastructure software like OS and VMM. Intel SGX is one of the most mature trusted computing solution on the market right now, compared to some other pure software solution like HE and federated learning. SGX secure enclaves are much more efficient. But it sounds very cool, but the hardware being secure doesn't mean that things built on it are automatically secure. If a software code itself is vulnerable, the data can still leak, like the hardware protections are not there at all. It is known that a large portion of the severe software vulnerabilities are caused by memory safety bugs. A lot of things have been done to deal with these bugs, but they just refuse to die. So there is now a new idea that instead of cleaning up the mess after the bug is there, how about preventing this bug from being created in the first place? The realization of that idea is from programming languages, which is Rust we are using right now. So software written in Rust is like immune to most memory safety vulnerabilities, like user-free buffer flow and so on and so forth. We realize the Intel SGX and Rust combined can form a great solution to trustworthy private data processing. So we developed the SGX enclave in Rust. If it compiles, it should be secure and trusted. This idea is already published in our previous work. We have enabled memory safe SGX enclave development in Rust and provided formal guarantee for several important memory safety properties. But modern software engineering is not just about writing your own code. Nowadays, all reasonably complex software has to develop on third-party libraries. The question is naturally raised: can enclave developers rely on in-stock third-party Rust libraries? Are they compatible with the SGX programming and security models? The answer is unfortunately no. SGX developer have to either import likely insecure third-party code or write everything from scratch. That's a problem we want to solve in this work. We want to build a supply chain of Rust libraries that are secure within SGX threat model to boost enclave development productivity. For the objective, we design a protocol to examine and audit third-party Rust libraries and securely port them into SGX. We built a highly automated framework to merge upstream changes to the ported version of the library, keeping them up to date. By the end of last year, we have ported 159 Rust libraries, which turned out to be extremely useful to the SGX Rust community. Here's what we achieved. By last October, we have ported the majority of the most popular open source Rust libraries into Rust and have kept them updated. These libraries are all manually audited to make sure they don't have break security requirements for SS enclaves. The majority of the work was done by a small team of like 3 engineers, which is very impressive. To understand our work have been helpful, we searched the entire GitHub and found that there are many projects already utilizing libraries from Rust crates, Rust libraries. We just counted mature projects maintained by a well-organized developer, so the impact is very solid, as you can see from this table. Okay, to conclude the presentation, I want to emphasize that the software supply chain security has become more and more important. This is particularly important to SGX, the trusted execution environment, and in our opinion, affects the adoption of the technology. We hope our work can help the advancement of trusted computing in protecting people's privacy without compromising the service we can offer them. The project I'm talking about has already been donated to the Apache Foundation, Software Foundation. Is under incubating in the Apache incubator. So all the source code and the project and the development document is open sourced online. So if you're interested in this project, you can visit the homepage https tclave.apache.org. Okay, thank you so much. I will take some questions. Josh?
All right, thank you for the talk, Mingshen. Let's see. So I'm not seeing any questions show up yet in Slido. Can you tell me more about the process of releasing the tool out of Baidu Research into the Apache incubator program, and how challenging that may be releasing such a tool out of a company like Baidu?
Yeah, that's a good question. And the motivation behind this is for either SGX or trusted computing community. The software or the supply chain or all the things not controlled by any companies at all, right? So the motivation behind this is we want to build an open community and attracts as many companies as possible, and to build up this trusted execution environment community. And the Apache Software Foundation is one of the most popular open source community right now in a very open way. So we decided to donate the code, document design, and human resources like me working on the open source project to Apache Foundation. And before becoming to the top level projects in Apache, like other projects, Hadoop, Spark, and so on and so forth, we need to go through incubation process. So that means we have to attract some other external contributors and have more activities on the open communities and really release the official, make some official releases under Apache Foundation. And then at that time we can discuss as a community to whether accept this project into the top level projects. So that's a whole process behind the open sourcing software to the Apache community.
Great, sounds exciting. So we have some questions from the audience. Okay. The first question, did you consider adapting this work to ARM's trusted execution environment?
Oh, that's a very good question. We already have did some progress on the ARM Trust Zone, and we have implemented the Trust Zone SDK, which is based on the open source the Trust Zone implementation OBTE OS. So as a trusted computing framework, we want to support as many backends as possible, like at Intel SGX, like ARM Trust Zone, and like RISC-V implementations or other implementations. So the first step is we understand that SGX is the most secure TE implementation among all other implementations right now. So our main development is on the SGX, and we already bring up the Trust Zone implementation and later we will provide a more compatible layer with other backends and provide a platform to other TE hardware implementations.
Okay, got it. So there's a second part follow-up to that question, which I think you touched upon to some extent, but the follow-up question was, is there any related work on ARM's trusted execution environment?
Yeah, it's already open source. You can search the name Rust OPTE Trust Zone SDK. So you can use Rust to write Trust Zone application and translate. And later we will also plan to donate this SDK to Apache Foundation to this TClay project so that we can support both SGX and Trust Zone.
Okay. So I'm not seeing any more questions popping up for Ming-Shen.
Okay.
So I'd like to thank you one more time, Ming-Shen, for the
thank you
for the nice talk. So before I close out this session, I would like to one, encourage the authors and presenters of this session to hang out in the video chat lobby to so that the audience can come in and talk to you potentially during the third hour of this particular time band. I also encourage the audience to visit the demos, attend the student research competition presentations, the Ask Me Anything session with John Grundy, and stop by the Google booth. So thank you. Enjoy the rest of the conference and have a good day.
Okay, hi everyone. So welcome to the P16 session. I'm Li Minzhang from UT Dallas. And there will be 5 fantastic presentations on security and learning in this session. And please note that there's a delay in the actual streaming service compared to the actual Zoom session where the speakers are in. So you may want to ask your questions on Clouder when we have them. Okay, so our first talk is about software visualization and deep transfer learning for effective software defect prediction. The presenter is Jin Chen. So Jin, you want to start now? Hello, Jin, can you hear me? Please start your screen sharing and unmute yourself. Hello. Oh, yes, great. Please. We can't hear you. We can't hear you. Sorry. Hey, Jin, we can't hear you. We cannot see your desktop. Okay, hey everyone, since there's a technical problem for the presenter's network environment, probably we'll go ahead and play the video for her. So Samia, please go ahead, play the video.
Is it me?
Yes, please. Thank you.
Okay. Hello, everyone. Good morning. My name is Chen Jinyi from Zhejiang University of Technology, Hangzhou, China. It's a great honor to give a presentation here. And our paper is titled Software Visualization and Deep Transfer Learning for Effective Software Defect Prediction. And first of all, I'd like to thank you, all our authors, especially thank you, bridge the gap. Professor. Hello? Is it me?
Yes, it's you.
Okay. First, I would like to introduce our work from 4 aspects, why we chose this topic and the main work we have done here. And the second, I will explain how the DTL-DP works from theory and experiments to expects. And finally, I will conclude the paper and point out some future work. First of all, as we all know, most prediction methods build prediction models based on modules in the source code and historical development historical. And then we will use these feature engineering tools to help us to extract the critical features. We wonder if we can tell those 2 programs are different in the image level. We can observe from these 2 images that both the semantic and the structural similarities between 2 programs can be effectively identified by visually comparing 2 program images. And from the surprising observations, we prepare to use an end-to-end deep learning transfer model as our basic method. First of all, we convert the files into images and use the deep learning models to automatically accomplish the feature extraction and classification. 2 extra strategies, transfer learning and also attention mechanisms are designed to improve the prediction performance. benefit from the transfer learning domain adaptation capacity. Cross-project defect prediction has achieved promising accuracy, scored as the state-of-the-art performance. The overall framework of our approach, deep transfer learning for prediction, is DTL-DP is shown in the figure. It is comprised of two stages. The first is the defect source code visualization, and the second is modeling with DTL. In the first stage, we use a visualization method to convert program files into images. In the second stage, we build a DTL model based on the AlexNet structure with transfer learning and self-attention layers to construct an end-to-end defect prediction framework. We use that framework to predict if a new file instance will be defected or not. In the source code visualization, we can see that 6 different kinds of images are constructed from one original file. This is because we had a data augmentation mechanism to improve the data quality. And the images produced in code images, each source file is converted into a vector of 8-bit unsigned integers corresponding to the ASCII decimal. Generate an image from that vector. We qualify the file size with the image size. After several times experiments and referred to some relevant papers, we conclude their relationship shown in the table. Modeling with DTL. The next stop, different from the original DAN model, the domain adaptation network model. We apply attention layer, specifically like here, combined with the loss, MMD loss, and also the cross entropy, in which case the MMD distance is used to measure the difference between two example distributions in the source domain and the target domain, while the cross entropy is to make the classification performance well. In the experiment part, before the experiments part, we also analyze the model sensitivity to the parameter choices. There are 3 critical parameters that are closely related to the model. From the simulation results, the 3 figures, we find out that the loss limitation is quite sensitive to the model performance, while the RGB perturbation selection has less impact on the performance. Finally, the proper image size is quite necessary. Here we brought up the first question. How does DTL-DP compare to the feature-based machine learning methods and AST-based deep learning methods in within project defect prediction tasks? We studied the distribution map of different methods for within project and concluded that the proposed method, DTL-DP, is most effective and it could improve the performance in within project tasks. Like other deep learners, it is quite sensitive to small sizes and unbalanced data. And the second question is, how does the proposed method compare to feature-based machine learning and AST-based deep learning methods in cross-project? And here we use the study. Finally, we have come 2 other questions, and the details can be referred in the paper. Finally, I'd like to thank you all the authors for their contribution to the work. Thank you for your attention. That's all my presentation. Thank you.
Okay, great. Thank you for the presentation. So I don't see any questions so far. Oh yeah, so there's actually one question on Clouder. So the question is, what is the granularity of the bug level? For example, did you label every bug file, every function, or every line? So what's the granularity for the preparing
every character in the code? Every character in the code, we transfer every character in the code into a pixel in the image. Use that as a feature, but the file has not been feature extracted manually or any other kind of tools. We just input the raw file into the model and use it automatically as a deep end-to-end model to extract the feature, to the attention layers to extract the weight, and finally use a fully connected layers to the classification task.
Yeah. So, but the question is, what do you use? Which granularity level do you use for labeling? So, for example, what's your prediction goal? Do you predict whether a file is buggy, whether a method is buggy, or whether a line is buggy? So, I guess it's a file level,
possibility, right? The possibility it will be buggy. We will give the buggy label or unbuggy label, clean label, with confidence.
Yeah, which level did you label those entities? Is it the file level or method level or function?
File level.
Like,
sorry, file level.
Yeah, sure.
File level.
Yeah. Okay, so another question, probably we can have it really fast. How sensitive is the approach to syntactic changes? For example, verbal renaming or reordering?
We use 10 data sets to testify the sensitivity to the files. Until now, we have found it not that sensitive to it.
Okay. There are coming more questions. Maybe you can take it offline. Okay.
Okay. Thank you. Thank you. Sorry for the delay. Sorry. Thank you.
It's fine. It happens the first time for all of us. Okay. Our second work is a general first paper. The title is Easy to Deploy API Extraction by Multi-Level Feature Embedding and Transfer Learning. Speaker is Su-Yu Ma. Please go ahead.
Hi, can you hear me?
Yes, we can hear you.
Okay, cool. So now I'm going to introduce our paper, Easy to Deploy API Extraction by Multi-Level Feature Embedding and Transfer Learning. Firstly, I'd like to talk about what is API. API is a set of definitions of functions or modules for building application software. There are some examples for API libraries, such as OpenGL, Pandas, NumPy, and there are also some API methods, such as NumPy.random, getBaseType, GL begin query. So what is API extraction? Well, distinguishing API mention from general natural language words in API documentation is referred as API extraction. In the following example, in this paragraph, we can see the iter is annotated because it is an API mention. And there is another example for API extraction from Stack Overflow. In this answer, we can see the set state and render are annotated because they are API mentions. And why is this task important? Well, API extraction is actually the prerequisite for many downstream applications, such as document linkage and domain-specific question and answering. And why is this task challenging? Well, firstly, API mentioned in formal software test usually like consistent writing forms and annotations. In the writing example, we can see the pandas is a function in apply is a function in pandas library, but it has many different writing forms. Secondly, API may have a common word simple name. In the following example, we can see in the first sentence, the apply is an API mention, but in the second sentence, the apply is just a common word. So we cannot just use rule-based method to distinguish API from the common words. As for the motivation, firstly, designers of a machine learning-based API extraction model have to manually select the most effective features for different libraries APIs, and some advanced features to boost the API extraction performance, such as word clusters and API gathers, have to be handcrafted. So we are motivated to design a neural architecture for API extraction in formal software test. And for the contribution, well, firstly, our work is forced to consider not only the performance of machine learning-based API extraction methods, but also the easy deploymentation of such methods. And we propose a multi-layered neural architecture to automatically learn to extract effective features from the input test for API extraction. We also adopt transfer learning to reduce the overhead of manual labeling of the training data. And we conduct extensive experiments to evaluate our architecture. And for the dataset, we selected 3,600 Stack Overflow posts of 6 libraries of 4 languages and we use Twitter tokenizer to tokenize the raw data. And after that, we manually label all this post data. Well, this is the architecture of our model. In our model, we mainly use 3 different feature embeddings. Firstly, we use the GLA word embedding to get the word level feature embedding that's in here. And then we use the correct level CNN to get the correct level feature embedding. That's this part. And we concat these 2 embeddings together. And we use the LSTM to get the sentence level feature embedding. And we use the softmax to predict if a token is an API or not. We also adopt transfer learning in our model. For instance, we use the NumPy post data to train an API extraction model, and we share the with to another model. And we use the React post data to fine-tuning this model to get a better performance. And in the experiments, we mainly discuss 4 questions. The first question is, how well can our neural architecture learn multi-level features from the input test? And we conclude that our neural architecture can extract effective multi-level features from the input test and support high-quality API extraction without using any handcraft advanced features. The second question is, what is the impact of the 3 feature extractors on the API extraction performance? And we conclude that all feature extractors are important for high-quality API extraction. In the third question, we discuss how effective is the transfer learning for adopting API extraction models across libraries of the same language. And we conclude that transfer learning can effectively boost the performance of the target language model with less demand on target library training data. In the last question, we discuss how effective is the transfer learning for adapting API extraction models across libraries of different languages. And we conclude that the transfer learning can still effectively boost the performance of the target language model. So that's all the content. Thanks for listening. Do you have any questions? Hi, can you hear me?
Okay, yeah. Sorry, I muted myself. So yeah. So thank you for the presentation. So let's see, do we have any questions on Clouder? Yeah, it seems there's no question for now, but actually very interesting talk. So I do have some questions by myself. So
Sure.
My first question is, yeah, so maybe actually I missed it, but you said that actually you manually determine the ground truth. So you manually label which are APIs, which are not APIs, right? So how do you actually ensure that the manual inspection is correct and you are not missing, you're not making any false positives or false negatives?
Actually, we have 3 people to one people will manually label some data, and the other 2 will check that to make sure the ground truth will be the right ground truth. So we we use double check.
Okay, thank you for the answer. Yeah. So my next question is, so it seems that the neural network architecture is kind of complicated. So how do you determine all the hyperparameters?
For this part, actually, we just use the set of different hyperparameters, and we choose the one with the best performance.
Okay, but you have to use a validation set, right? You cannot directly use the best performance on the testing set.
Oh yeah, sure.
Okay,
we use the validation data set.
Okay, time's up. Thank you for the talk and thank you for the answers. Okay, so let's move on to the next talk. So you can stop your screen sharing. Okay, please stop your screen sharing. So our next talk is a technical paper. How does misconfiguration of analytic service compromise mobile privacy? The speaker is Xuelin Zhang. So please start. Hello, Xuelin. Can you start now?
I'm gonna share my screen.
Wonderful.
Okay. Can you see my screen?
Yes, we do see that.
Okay. Okay, hello everyone. My name is Xuelin. I'm a PhD student at University of Texas at San Antonio. Today, I'm going to talk about our work, how does misconfiguration of analytics service compromise mobile privacy? This is a collaboration work between UTSA and CMU. I wanted to start by discussing the analytics service and what motivated this work. Analytics service has been widely utilized to track users' behavior on mobile apps. The collected user behavior data is valuable for the app company to understand how their app works and what they can do to improve it. Let's see how it works. When a user is interacting with an app that connected to an analytics server, users' behavior data will be collected. They're basically everything the user does within the app, like which button the user just clicked. On the other hand, users' other information like demographic data can also be collected. We call them as users' attributes, like users' location, age, and gender. For example, the app company may want to know the age distribution of their users and how the behavior is different among different age groups. One thing that we need to know about is that the attribute collection is just for statistical purpose, but not for any specific individual. So when the behavior and attributes data have been collected, analytics service will generate the report for the app company so that they can improve their application. At the same time, analytics service might collaborate with some advertising service to deliver targeted ads. So basically, analytics service is pretty helpful for the app company collecting data. However, incorrectly configured the service might result in privacy risks. Recall that app developer could configure the tracking of the user's behavior along with users' attributes, where the user's attributes are not supposed to be any identifiable or sensitive information like social security number or phone number. An example of misconfiguration would be using sensitive information like email address or phone number as the user's attributes. In this case, the analytics service will receive those data and then put them into their behavior report. This leads to an identifiable behavior report. So basically they know who you are and they know everything you did on that app. Isn't this scary? Sounds like there's no privacy at all. So it is important that when app developer configuring the analytics service, they should avoid using sensitive information. And actually there are some requirements from the service provider. For example, Google's Firebase, which is the most popular analytics service, has the following statement. When you set user properties, be sure to never include personally identifiable information, such as names, social security numbers, or email address, even in hashed form. There's a similar suggestion from another popular analytics service provider called Flurry. So we can see that they made it very clear that do not use any sensitive information as users' attributes. So the question is whether app developers always follow them in reality. So now we understand there are privacy concerns in analytics service configuration. We can start asking questions. We started with 4 research questions. What configuration options do analytics service provide? And how commonly do app developers use PAI as users' attributes? Do analytics service provide any mechanism to detect and prevent such misconfiguration? Does the misconfiguration violate any policy? To get to those questions, we needed to start by looking into how to configure the user's attributes. We learned that analytics service usually provides specific methods that allow app developers to set attributes for their users. We refer to those methods as attribute setting methods, or ASMs. For example, set user identifier. This method allows app developer to set the unique ID for the individual using the app. Another example is set properties. Basically, it allows us to set anything that we need. So an example of misconfiguration would be using a phone number as user's identifier, or put the email address into the user's property. So knowing the ways to do the configuration, we developed a semi-automatic approach to detect such misconfiguration. And we evaluated the most popular 1,000 Google Play Store apps that contain at least one ASM invocation in their code. So in our approach, we started by looking at the documentation of the most popular analytics services. We collected the attribute setting method from them. And also to perform the study, we need to create a user profile, include a real Gmail account and the device identifiers from our test mobile device, a fake username and phone name. Then for each app, we decompiled the APK file and instrumented the ASM within the app. And then we performed a runtime UI testing using the predefined user profile. Then later in the system log, we're able to detect the misconfiguration by comparing the parameters that pass into those ASMs with our predefined user profile. So please take a look at the paper if you are interested in the detail of our implementation. So let's talk about our findings. So for that first question, we're trying to find what configuration options do analytic service provide. As the chart shows, we categorized the ASMs we collected into those 7 types. And also, each column shows how many apps actually invoked those ASM during runtime testing among the 1,000 apps that under study. We can see that a significant number of apps were using those ASMs. Okay, moving on. The second question is how many of the apps misconfigured the analytic service by using PII as users' attributes. Our study result shows that there are 120 apps used PII, including email address, username, IMEI, serial number, and the most commonly one is Android ID. So getting to the third question, do analytic service provide mechanisms to detect and prevent misconfiguration? It is very challenging to tell how the data is stored and proceed on the server of the analytic service. However, we can predict their practice from the behavior report they generate for the developers. We found that whatever is provided through the ASM will be directly linked to the behavior report without any encryption. Here's a sample report. We see that here's a sample report. We see that user email, username, and ID are presented in the report without any anonymization. Another sample report is showing the user's ID, latitude, and longitude. So this means that analytics service did not prevent the misconfiguration. Okay, the last question. Do analytics service misconfiguration violate any policy? Well, by inspecting the privacy policy of the 120 apps that have misconfiguration issue, we found that 27 of them may violated their own privacy policy. Also, 31 of them may violated the requirement from the analytics service. If you are interested in all of those data, you can find everything in our website. So what did we learn from all of this? We believe that misconfiguration could bring big privacy risks, and current enforcement efforts are just not sufficient yet to address the problem that we're facing. We have some recommendations for the future. First, enforcement is needed to prevent the misconfiguration. It could from multiple parties, from the app company, from the Android system, from the analytics service, or even a third-party auditor. And second, we think static analysis techniques are desired to detect the data flow from the PII to the ASMs. But one challenge is to detect the PII sources. Now I can take some questions. Thank you.
Okay, thank you for the great talk. So yeah, let's see if there are any question yet. Okay, we do have a question, anonymized question for now. Do you release the source code of your implementation?
Yes, we do have the everything, the source code and the data, the app, the report, everything on our website. Okay, awesome. So, okay, it seems there's no other question. Okay, I have some questions. Sure, go ahead.
So, okay, so one thing is how do you determine the ground truth that whether your app does leak, some important information? Did you just use some script to exactly match the email, the fake email address you generated, or what do you do?
So basically, first, we do a runtime testing to make sure that the sensitive information we're passing to those attribute setting methods. So you see that we have some methods that are provided for the app developer, right? And then we instrument those apps and try to print out the parameter that's passing to those apps during runtime. And then we have a virtual user, we have everything like account, like device identifiers. And then we play with that app. We'll play with the app using those predefined user profiles. Then we printed out all the information that we need in the system log. So later in the system log, we can just search the keywords of the user profile. Like let's say we have an email is utsaresearch@gmail.com. And then we search that keyword in the system log. If we found one of the setting method is using this email, then we can confirm that, okay, this app is using user's email address as a user's attributes.
Yeah, I guess in that case, you want your fake information to be as strange as possible, because otherwise,
exactly,
overlap with actual system log, right?
Right,
okay,
right, yeah.
Yeah. Any other question for now? Okay, I do have another question by myself. So it seems that you did use some dynamic UI testing techniques to play with the app, not manually, but with techniques, right? So what kind of detailed technique did you use to test to run the apps in the runtime to trace all those logs?
So there are two types of apps. Some apps that do not require registration, you can just open it without any account information. For that kind of simple app, we just use Monkey to run the test about 20 seconds or something. But for the apps that requires registration, we manually log into it.
Okay, but then after you log into it, you can continue with Monkey, right?
Yes, exactly.
Oh, okay, awesome. Okay, great. Thank you again for the great talk.
Thank you.
So, okay,
I'm
you
just
can
gonna stop the share. Okay.
Yeah. So let's move on to the next talk, securing unsafe Rust programs with XRust. The presenter is Pei-Ming Liu from Taimu. So Pei-Ming, you can start now.
Okay. Can you see my screen?
Yes.
Okay, so I'll just start. So hello everyone, my name is Pei-Ming Liu. I'm a PhD student from Texas A&M University, and I will present our work on securing the unsafe Rust program with XRust. So for those who might not be very familiar with Rust, Rust is a relatively new system programming language that guarantees the memory safety and the free of data rates statically through type checking. As a promising system programming language and a good alternative to C and C++, Rust is gaining its popularity in the industry. And you might also saw some works that I presented previously. And as you can see, it's now widely adopted inside Microsoft, Amazon, and Cloudflare, as well as Facebook, which choose Rust to be the programming language for the Libra blockchain project. So it seems like the memory safety issue has been beautifully resolved by Rust. But unfortunately, Rust have a dark side called unsafe Rust, which opens a security hole to the whole Rust type system. It allows bugs to escape from the static checking performed by the Rust compilers. Unsafe Rust is needed, as Rust static checking is sometimes too strict to admit even valid programs, as static analysis by nature is conservative. The example code snippet collected from Rust base 64 implementation shows you real-world vulnerabilities that caused by unsafe Rust. As you can learn from the slides, you can basically do pointer arithmetic, memory access on the pointers without bound checking, just like you can do it in C and C++. So this eventually can lead to memory overflows. And actually, similar bugs has also recently been discovered due to the use of unsafe Rust. This one is a buffer overflow bugs in the Rust vector DQ in its standard library, and there's another one in its string implementation. Yeah, those two are real buffer overflow bugs due to the use of unsafe Rust. And to understand how unsafe Rust is used in real-world application and to motivate our approach, we did an empirical study on 500 randomly selected Rust programs. We analyzed the portion of unsafe Rust used by them. The result shows that only 1% of the Rust code is actually written in unsafe Rust, and actually 99% of code written in safe Rust. However, although most of the code is statically protected by the Rust type system and is guaranteed to be memory safe, the 1% unsafe Rust can still lead to huge security threat to the entire program, just like the example we presented in the previous slides, as Rust does not put any limitations on the execution of unsafe Rust. So here we want to introduce our solution. We call it XRust, which is trying to mitigate the security threat brought by the unsafe Rust. The goal of our method is to isolate the side effect caused by unsafe Rust. It is achieved by ensuring that memory corruptions introduced by unsafe Rust won't escape the memory region that is allowed to be accessed by unsafe Rust. So that most of the object, as we already did in empirical study, in the Rust program cannot be damaged by the use of unsafe Rust. We aimed at a practical method that cause negligible overhead to the applications. So XRust does not attempt to provide full memory safeties, as those techniques, such as data flow integrity and softbound, are usually too expensive to be deployed in practice. So we, as shown in this slide, at a high level, XRust aims to transform the original program on the left-hand side to the protected program on the right-hand side at compilation time. In this example, since the vector named buff is manipulated in unsafe Rust at line 7, it is identified as an unsafe Rust by XRust. So for those unsafe objects, we allocated them into a different memory region to isolate them from safe object. The runtime checks are inserted to guarantee that access on unsafe object cannot escape the unsafe memory region. As a result, the memory corruption on buff cannot damage the integrities of safe objects, such as the password in this example. So there are 3 key components in XRust. The first one is an extended Rust and Rust compilers that support unsafe object at language level. And the second one is the runtime protection technique used to isolate the side effect from unsafe Rust. And the third component is an extended heap allocator that manages 2 memory regions separately for safe and unsafe object, respectively. So in our implementation, we did to support allocations in unsafe heap region at language levels. We made extensive modification to the Rust compilers. We add new operators called unsafe box to the Rust language, and we extended some fundamental APIs in Rust standard libraries. And to have a heap allocator that manages 2 memory heap regions, we extended ptmalloc, which is the default allocator for glibc. In our implementation, we reused most of their design and data structures, but we added a new heap arena to manage unsafe object. So to identify the identification of unsafe Rust of unsafe object is done by a data flow analysis by treating each memory allocation site as source and every access in the unsafe Rust at the sink, and to reason whether there is a data flow from the source and sink. And we provide 2 types of runtime enforcement technique. The first one is instrumentation, which basically insert assertion between access on unsafe Rust to guarantee the safety. And the second method is to insert inaccessible memory page between safe and unsafe heap region. And for multi-threaded programs, we aim to isolate the side effect from unsafe Rust by ensuring that the address that has been used to hold an unsafe object will not be reclaimed and reused for holding another safe object. In this way, we can avoid time of check to time of use attack. So in terms of performance, we compare our method with a complete solution DFI, and our result shows that when using instrumentation, XRust only impose like 3% overhead on median and about 20% overhead on average. When using garbage, the overhead is actually negligible with like less than 1% overhead on median and about 2% overhead on average. On the other hand, you can see DFI imposes more than 4 times slowdown on the target program. So our result also shows that to support and separate heap region for heap allocator, it would not cause too much memory slowdown as well. Only 5% overhead is imposed on the intensive testing. So to evaluate the effectiveness, we did a proof of contact attack on real-world vulnerabilities, and our result shows that XRust is capable of defending them all. And for more detail about the experiment setup and how we perform the attack and also the implementation of XRust, please refer to our paper. I think that's all for my presentation. Any questions?
Okay, thank you for the great talk. So, okay, there's no question for now. So yeah, again, I encourage you to ask question earlier because there's a delay in the actual streaming service compared to our actual Zoom session. So, but okay, so I do have some question. Oh yeah, so there's a question popping up. So the question is, what if there are some pointers pointing to the safe object, but unsafe region? So it may still impact the safe code, I guess. So what's your answer to this question?
Can you say that again? I don't quite get.
Oh yeah, sure. So I guess you can also see that on Clouder. So the question is, what if there are some pointers pointing to the safe object, but unsafe region?
Oh, actually, in that way, then it's not a safe object. By definition, then it becomes an unsafe object. I think you can refer to paper about like more accurate definition on unsafe object. Basically, when we regard something as unsafe object is whenever there's a data flow from the object, whenever the object have the chance to be manipulated by unsafe Rust. So in this case, it's not going to happen because this is unsafe object by definition and will be protected by our method. Yeah. Does that?
Okay, do I also have some questions? So actually you said that you give up the actual full memory safety for the sake of efficiency, right?
Yeah,
what kind of issues you cannot handle, the current implementation cannot handle?
Yeah. Actually, this one, the XROS is more like in address space memory isolation technique. It does not it does not, let's say if you have a crash due to unsafe routes, it does not prevent that. And if the let's say the buffer flow corrupt another unsafe object, we do not protect them as well. Our assumption is that most of objects like in the program are actually safe. So we want to isolate the side effect from those like memory corruption that may exist in the unsafe region from affecting safe objects. So in summary, we do not protect any like internal overflow within the unsafe region. Yeah. So it can still damage other unsafe objects.
Okay, thank you. Yeah, I just have a question regarding you mentioned that you have some data flow analysis to determine the actual sources and sinks.
Yeah,
so what kind of data flow analysis do you actually apply? Is that context, flow, field sensitive?
Oh, yeah.
Interprocedural? Yeah.
Yeah, we actually using an existing framework called Faster. You may heard of it. We run a context insensitive data flow analysis. Yeah.
Okay, thank you. Yeah, great. Yeah. Okay, thank you again. So we can move on to the last talk of this session. This is again a technical paper on is Rust used safely by software developers. And this is going to be presented by Anna Nora Evans. So Anna, it's your turn.
Hello. Can you see my screen?
Yeah, we can see it, but we see too much. We also saw your actual script. So now it's the presenter view.
Oh, okay. Sorry. Okay. Are you good now?
Yeah, we're good now.
Okay. So thank you for attending my talk. I performed this work with Professors Meryl Sofa and Brad Campbell, and we were interested in how Rust developers are using Rust. And there is a little bit of a review from the previous talk. Rust has two competing goals. First, it aims at being a safe language. It guarantees memory safety and data race freedom. And on the other end, it aims to be an efficient and programming language and be as fast as C. Thus, Rust occupies a happy medium between safe languages and C, wanting to be safer than C and as fast as C. And one of the inventors of the Rust language called this approach pragmatic safety, meaning that you can break the static rules, but you have to say that you're doing it. And that is done in the language by using the keyword unsafe. However, it is in a standard way by the use of unsafe, but it's not easy to audit. An unsafe block can be anywhere in the code, and you have to track it down through a long list of dependencies. And thus, unsafe Rust is simply safe Rust with some extra powers, and that's why it has to be marked as unsafe. The code may still be memory safe and data race free, but we have to trust the programmer. And okay, now we may wonder, why would we have this? Because it's necessary to be a low-level programming language. It has to, you need unsafe for device drivers to implement an operating system or even communicate with one. Our research focused on trying to find out how often and what unsafe operations do Rust developers use in practice, and what is the impact of unsafe use on the static safety guarantees of the Rust ecosystem. There is a little bit of terminology. A Rust library is called a crate. The Rust language comes with a very small set of basic libraries, and everything else is available in a central repository that is called crates.io. And it is interesting that the numbers of crates available doubled since September 2018, so it is a very popular programming language. Here, we made up an example to show you the problems that a developer might encounter in tracing down the unsafe. And let's say that we develop library 1, where function foo should call function bar from library 2. Here, in this function library 2, hasBuzz is an interface, so it can be implemented either in library 3 or library 5. And in turn, library 5 calls the Cox function of the library 4. And the dependency graph of the libraries is shown here. And now we're looking at how is this unsafety affecting the system. We start from the end of the call chain and we looked at the function Quax. This function is declared unsafe by the programmer. And then library 5 is required to make the call from an unsafe block to mark that block. And then, however, from the outside, just by looking at the signature of function buzz, you can't tell whether unsafe is used or not. And so we define these kind of functions that look safe from the outside, possibly unsafe functions. And then again, when we moved back to the bar function in library 2, now this function could be safe. It calls buzz from library 3 or possibly unsafe from library 5, and then it moves back. And what we executed is a large-scale empirical study. We analyzed the majority of the available Rust libraries, and we also looked at a smaller subset of libraries that account for about 90% of the downloads. And the good news about this set is that is only a little over 500 crates. So there's a small number of crates that has a big impact. For our analysis, we assume that the standard library safe functions are safe unless they're explicitly marked as unsafe, and that the compiler generated unsafe code is safe. So basically, we trust the compiler. We develop an analysis to figure out the how much code becomes unsafe by calling through the function calls. And we define a function as possibly unsafe if it contains an unsafe block or it calls another possibly unsafe function. To build a precise call graph, it's not completely possible because of parametric and runtime polymorphism. So then when we can't find out what exactly the function call will be, we perform two analyses, a conservative one where we assume that the call is possibly unsafe, and an optimistic one where the call is assumed safe. So we get upper and lower bounds. Now, moving on to the results, we do observe that less than 30% of the crates use an unsafe block. And it is more popular in the most downloaded crates. Now, looking at functions that are declared unsafe, we observe that only 20% of the crates have an unsafe function. This means that the rest of the 80% of the crates look perfectly safe. However, when we use our analysis, we observe that actually less than 50% are entirely safe Rust, but 80% of them seem safe. So the impact of unsafe is significant. We further look in more detail what kind of unsafe operations are possible and how often they're used. The dereferencing of a C-style pointer was discussed thoroughly in the previous talk. Another reason for that, for an unsafe operation, is that it's a call of an unsafe function. What we observed is that the unsafe function calls account for the majority of the unsafe operations, and the dereferencing of a C-style pointer is still significant. Other sources are less important. We looked even deeper. We looked at what kind of language these unsafe functions are implemented in. And we found out that a C is not a major source of unsafety. Re-implementing C libraries in Rust will not give us would not get rid of the unsafe. And the Rust functions and compiler intrinsics are the majority of the unsafe calls. We looked at the change in the use of unsafe over time. We started this project in the September 2018, and by the end, a lot of things happened in Rust. One of them was Rust 2018 was released, and the unsafe guideline working group became extremely active. But we noticed that in spite of all these changes, the most downloaded crates did not have a change in unsafe use. Based on our findings, we make the following recommendations. There should be a mechanism, and developers should be encouraged to define pre and post conditions for all these declared unsafe functions. To make it easy for the programmer to understand where unsafe is used, the compiler should print a warning with a call chain that can result in execution of an unsafe operation. Furthermore, the center to make it even easier for the programmers, the central repository should make it easier to understand what crates are using unsafe by using a tag or a badge, and maintain a dependency tree for each library with chasing down where unsafe is used and being clearly marked. And one of the reasons for the pragmatic safety at the beginning of the talk was that the developer should decide for themselves how much unsafe they're comfortable with, but most of the novice programmers will not be able to perhaps understand all the intricacies. And so it will be useful to maintain a list of code reviews of this unsafe Rust so that the programmer is able to trust some other experienced programmers. In summary, we performed a large-scale study of unsafe use in Rust. We found out that the majority of the crates are not guaranteed by the compiler to be memory safe and data race free, and that unsafe function calls are the most common use of unsafe. We also compiled a set of recommendations to enhance the Rust compiler and ecosystem. Thank you.
Okay, great. Thank you for the nice presentation. So we have 1 minute, but we can still ask a quick question. Okay, there's no question on Clouder. So I have a quick question. So it's great to, to learn about the current status of the use of unsafe Rust code from your study. So I'm just curious, because I don't do research in Rust. I'm just curious, how often do those unsafe Rust code lead to real-world issues, real-world vulnerabilities?
So there was a few actually security vulnerabilities discovered. So there is a real issue. I don't have an answer to your question precisely how often it leads to a vulnerability, but it's better to be upfront about it rather than demonizing people that use unsafe.
Sure. So I mean, later on, maybe it's like interesting to actually link the unsafe Rust code with the previous bug bug fix history or something like that to actually further analyze those code in more details. Right.
Yes.
Okay, great. Thank you so much for the nice presentation. Okay, so this is the end for our session. And thank you all for attending. Thank all our speakers, all volunteers, and this concludes our session. So bye-bye.